Well, SpongeBob is not back yet, but that proportionality lesson reminded me of a good application for proportionality. So I'm going to deal with proportionality as it relates to shapes. Specifically here, similar shapes. So we'll talk about that here in just a second. The diagram shows a door that has a window in it. So we can see the door, we can see the window. The front faces of the door and the window are similar rectangles. I guess it'd help if you could read that, huh? That have the dimensions shown. So the window's 60 across, the door is 84 across. The door is 210 tall. The window is called H. We don't know that one yet. It asks us what is H, the height of the window in centimeters. And so similar figures here means something very specific. It means in non-math words, we could say same shape but different size. In other words, this rectangle would exactly match this rectangle if you just made it bigger. Not stretched it, right? Not make it longer this way without making it taller. Not stretch it taller this way without making it longer. But if you just zoomed in on it, made it bigger, these would be exactly the same. So that's interesting, and it's got a cool math abbreviation. So let's look at these two triangles, because these will be easy to draw. Anytime I have similar, there's that word again, shapes, I can think of them as wearing little baseball caps. If I could draw baseball caps, that would be better. And the reason I draw baseball caps is because there's an acronym I like to use. Similar shapes wear caps because they have congruent angles and proportional sides. And so you can see how that last lesson reminded me of this, because here's that word proportional again. And so something cool that we didn't really talk about on that last lesson was that proportional means they're going to change in the same way. So this one here is 15. This one here is 5. Well, if you've got your math facts, your multiplication facts memorized, you know that 15 is just 3 times bigger. And so proportional sides here means that however you change one, you're going to change the others the same way. So if this side got 3 times bigger, then all 3 sides, and for a different shape, all however many sides there are sides, they all got 3 times bigger. And what's cool is they're not only related to each other in the same way, but they're related to themselves in the same way. So in other words, if I look at 5 and 3, just in general, I won't make you do the exact math, but 5 is a little less than half. Nope, 3 is a little more than half of 5, right? 3 times 2 would be 6. So these sides are going to be related in that same way, no matter how big or small I shrink or grow this triangle. In other words, if I take the bottom number times 2, it'll be just a little more than this side number. 9 times 2 is 18, a little more than 15. Now, if we find the exact ratio, in other words, 3 times what number exactly gives me 5, then that's always going to work. No matter which of these triangles I'm on, whatever I use to get from the bottom to the slanted side, I can multiply by that exact same number. So if I have a big set of these, that's cool because I just look at one number and how it's related to the other two, and I multiply them that way. Okay. So we're going to look at this one here in a minute. I just wanted a picture I could actually draw these caps on. Congruent angles, and congruent here means equal, right? It's the geometry term for equal. So this angle right here and that one are exactly the same. They're congruent. They don't just relate in the same way, which is proportional, but they're literally the same. If you cut this out and picked it up and stuck it right here, at the very tip where they line up perfectly. If you cut it out and stuck it here, those line up perfectly. You can see the corners here, those are identical right angles. So just remember, similar sides, or I should say similar shapes, wear baseball caps. Congruent angles, proportional sides. So there's not a lot of room to draw it here, but I could draw the caps on the doors because they do have congruent angles, and I can see here they're all 90-degree angles everywhere, and these all exactly match each other. And then the proportional sides business. Okay, that's what's going to help us here. Remember that 84 and 210 are related in the same way that 60 and the height are related. And then I can also say that 84 and 60 are related in the same way that 210 and the height are related. So I have these relationships within the same shape. Door to door will match window to window, and also across shapes. So height to height will match base to base. Which seems a little crazy if I'm just trying to look at that and guess which of these numbers it is. But if I actually put down the math, it's not bad at all. How did I turn 84 into 60? Well, sadly, there's no like easy multiplication problem. But anything times 1 is itself, right? So think what we could do to this 84. We could divide it by 84. Well, that would give us 1. And then multiply it by 60. Now, why did I write it like a fraction? Because when I multiply by a fraction, it's like multiplying by the top number and dividing by the bottom number. Huh? And that's going to be the same relationship as if I took 210 and turned it into h. 210, okay, so I divide it by 210. I'm going to get 1, because then I just have to do 1 times h to get h. And so I can set up what here is called a proportion. A proportion just means two fractions equal to each other. Okay? So I reasoned out where those numbers came from. A cool shortcut, as far as your thinking goes, is to just label everything. These top two numbers both came from the window. 60 is on the window, h is on the window. These bottom two numbers, those both came from the door. 210 is on the door, 84 is on the door. But we're not done labeling. I only labeled half of everything. There's 4 things going on, so I have a top and a bottom, check. Don't forget to also label the left side. Where do 60 and 84 both come from? They both come from the base. So those have matching labels. Where do height and 210 both come from? Those both come from the height. So anytime you're dealing with proportional relationships and missing sides, you want to make sure you have this set up so that everything, top, bottom, left, and right, all have matching labels. Because if you put the numbers in the wrong spot, you're going to get the wrong math. Okay? So this makes sense, right? The height of the door is where this height line and this door line intersect. 210. How about the height of the window? Well, that's what we don't know. That's h. The base of the window, though, is where the base and the window intersect. We know the base of the window is 60. And then the base of the door is 84. Okay. So this is the setup. If you're super sneaky, you probably already figured out how to guess which of these answers it is. But because they're evil, a guess isn't going to be good enough here. We better find out exactly what it is. So we're going to have to solve this using something called the butterfly method. So I assume all of you are familiar with butterflies. And hey there, little guy. Are you here to investigate butterflies? No. You can talk? No. You definitely can talk. You're just talking right now. No, thank you. Are you like a little talking pencil sharpener? Yes. Do you have any pencils? I don't. Well, that was weird. What were we talking about? Oh, the math. Okay. What I want to do is rewrite this. The labels are super helpful for labeling. I just want a little more room to do the math. When I have it set up like this, I'm going to draw a butterfly. So a butterfly's body is in the middle, right? So if I'm looking at the middle here, then there's an equal sign in the middle of the butterfly's body. So the first thing I should do is make sure that the butterfly has a whole body and not just half a body. Nobody's ever seen like a stumpy little butterfly with a short body, right? They're all stretched out. So I've got equal signs in the middle of my butterfly. And then I'm going to draw wings. I'm going to go bottom right to top left. Make the wing look like that. And then bottom left to top right. Make this wing look like that. And what these arrows are doing is multiplying. So here I have 210 times 60. Okay, so I'm going to have to do some math here. Math is easy. It will be 1,260. You sure about that? Of course. 1,260, huh? Correct. The answer will be... No, don't tell me the answer yet. Do you have any pencils to sharpen? No, I still don't have any pencils. I've been sitting right here since the last time you asked. Yeah, so 210 times 60. This should... That robot lied to me. There should be 2 zeros at the end. 210 times 60. I got a 0 for everything here. And then a 0 here. 6 times 1, 6 times 2. So I'm looking at 12,000, not 1,000. Never believe a robot. 84 times h. Well, don't forget, there's an easy way to write that. 84 times h. I don't have to write the time sign, a number written next to a letter, secret hidden multiplication sign. Okay? So if I take h times 84, I'll get 12,600. Well, I don't want to take h and times 84. I want to just know what h is by itself, not times 84. So I'm going to take everything, I'm going to divide it by 84, and then the answer is going to be, what do you want? You want me to find the answer? No, I don't want you to find the answer. You messed this one up. Get out of here. Okay, so we're going to take... Do you have a pencil to sharpen? No, I don't have a pencil to sharpen. 12,600 divided by 84. 84 can't go into 1. If I have 1 cookie, I can't share it with 84 kids. It's not going to work. If I have 12 cookies, I still can't share it with 84 kids. If I have 126, that'll work. Every kid can get a cookie. I'll use up 84 of my cookies. And I'll still have I'll have 42 cookies left over. Which would be fine if it were like real life and I could eat the cookies. But it's not, so I got to keep dividing. Bring this 0 down. How many times can 8 go into 420? Well, look, it's probably either 8 or 5. So let's hope for the best. If I put a 5 up here, 5 times 4 is 20. 5 times 8 is 40, plus 2 is 42. That gets me all the cookies, but don't forget, this 0 still matters, and I have to say, well, I have no cookies left to share with that 0. So it is, in fact, 150. And again, if you want to check this math, figure out what could I multiply 150 by, and we'll go basically the opposite way from these arrows, right? Go from the small number to the big number. 150 times what equals 210? That's going to be the same exact number you can multiply 60 by to get 84. And then you could do it the other way also. 60 times what number would give me 150. That's going to be the same number I could multiply 84 by to get 210. That's what being proportional means. Down here, triangle RST. RST going from here to here to here. And then obviously it's a triangle, so don't forget to connect it back to the beginning. It's similar to triangle RVW. Wait a minute. So these triangles overlap. That's totally fine. We still use all the same rules. These triangles are wearing matching caps. Again, I apologize for the terrible drawings, but the angles are going to be congruent. I got congruent angles, and the sides are going to be proportional sides. Okay? So whatever number I multiply d by to get 18, that's the same number I can multiply 10 by to get, be careful here, I'm going from the blue side to the yellow side. So I'm not multiplying 10 to get 15. I'm multiplying 10 to get, sorry, I'm not multiplying 10 to get 5, because 5 isn't the yellow side. The whole yellow side, which I was thinking about and totally just gave away to you, is 15. So that's what I got to multiply. Question is, what number is that? Well, 10 times what gives me 15? There's not like a math fact for that, so let's use our trick like we did up here. If I take 10 and divide it by 10, it's 1, and then I just have to multiply it by 15. I set up my proportion, and now let's just make sure that all of these labels match. 15 came from the yellow triangle, which here is RST. And 10 came from the blue triangle, which here, even though I forgot to highlight it for us, is RVW. And in fact, I can make our lives easy and label these RVW in blue and RST in yellow. Okay. So don't forget, they have to match not only tops and bottoms, but also lefts and rights. So do 15 and 10 match? Well, they sure do. They both came from the left side. And so now, look at this other information I have. I'm missing D. D needs to be somewhere. I know that anything from the blue triangle is going to go on the bottom. So I'm going to put D right there. And it's related to 18 because those are both the bottom number from the triangle. And I do this again in elaborate detail because this is probably the most important and easiest to mess up when you're solving proportions. If you don't make sure that all four have matching labels, all four sides means left and right, top and bottom, then you're not going to get the math right. Okay? So I have it set up like that. I need to do a butterfly, so I'm going to redraw the butterfly down at the bottom. Yes. Do you have a pencil to show? I don't have any. I've got markers, and I don't have a pencil. I have nothing for you to sharpen. I've got nothing. Do you have a pencil? I don't have a pencil. So, rewrite this proportion so I can solve it using the butterfly. Body of the butterfly has got to stretch from the top of the butterfly to the bottom of the butterfly. And then I multiply bottom right times top left, bottom left times top right. 18 times 10 is going to be 180. 15 times D is going to be 15 times D. I said 15 times D. I wrote 15D. Remember, that's the same. I know it's times. I don't have to write it. And then I don't need 15 groups of D. I just need one group of D. So I got to divide both of these by 15. 15 into 180 is going to give me, I can't go into 1, I can go into 18 one time. I'll use 15 of those cookies. I'll have this 0 come down. Looks like 12. Zoop. So the setup, the butterfly. That's all there is to these proportional problems. What if they're evil and they don't give you a picture? Well, obviously it's evil, but let's see if it's any harder. Anna drew a map of the Panama Canal. In the scale Anna used for the map, 4 centimeters represents 20 kilometers. The actual length of the Panama Canal is 82 kilometers. What is the length in centimeters of the Panama Canal on Anna's map? Anytime you see 3 different numbers in a problem, you should be highly suspicious that this is a proportional problem. And the way you know for sure is if you can set up the proportion and it works, it's a proportion problem. Remember, a proportion is just 2 fractions equal to each other. So I start going through and blah, 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 blah. The first number I see, I'll put right here. This is in the scale Anna used for the map. So I know 4 is part of the scale. Put that on top here. These are going to be all my scale numbers. Remember, the labels have to match. So whatever else I see on the scale, I'm going to put on top. And then I also see the 4 is in centimeters. So I'm going to go ahead and label this one on the left, my centimeters. Any centimeter numbers, I'm going to put on the left. It says it represents 20 kilometers. What does? Oh, well, I'm still talking about the scale. So the 20 kilometers also gets to go on top, which is perfect because it couldn't have gone on the left where my centimeters are. This is going to be kilometers. The actual length of the Panama Canal. So now I'm not talking about the scale, I'm talking about the canal. So those are my bottom numbers. 82 kilometers. Well, look where my kilometer numbers go. What's the length in centimeters of the Panama Canal, bottom numbers, on Anna's map? Oh, her map, which is in centimeters. This is what I don't know. And so I just have to butterfly this out. Equal sign in the middle. 82 times 4, which would be 82 times 2 is 164, times 2 again would be 328. 328 equals 20x. So I have to divide this by 20. 328 divided by 20. Can't go into 3, can go once into 32. I'll use up 20 of those. I got 12 left, so I bring down this 8. And I'm looking at 6, which would be 120 even. I still have 8 left over. Since I have decimal numbers, that's not a problem. I just put decimal numbers here as if it were $328. Put my decimal up top too to show that I've used it. And then, once it's written, I can ignore it. I pretend this is 80, not 8.0. Can 20 go into 80? Sure, 4 times. There we go. Okay. So, same thing. Picture or not, you just find the things that match. You set up the proportion. You solve the proportion. So, Corbin made a scale model. Do you have any pencils? No, I don't have any pencils. He made a scale model of the San Jacinto Monument. The monument has an actual height of 604 feet. Okay, I see a number. Let me write a number. 604 feet. And then my labels here. I guess I don't need a fraction quite that big. This is going to be the actual height of the monument. So, monument here, actual height here. No, height. So my height's going to be everything on the left. My monument's going to be everything on top. And so I'll need something different from height and something different from monument. Well, Corbin's model used a scale. Perfect. The actual monument will be on top. The scale will be on bottom, in which 1 inch. Okay, so I now have... let me think. The scale numbers. What is the height in inches? Let's change these labels. We'll do height over here. This will be, yeah, that'll work. we'll put the scale on the bottom instead. And this will be inches on the bottom because the actual height is in feet. And so now if I have feet on top, oh, well, there's my foot number. And from the scale, that's going to be 1 on the bottom. And so you see, I don't have to like change the inches into feet when I put them in this math problem. The fact that they're labeled this way makes sense. What's the height? So I'm over here on the left side in inches, so I'm down on the bottom of Corbin's model. Voila. So butterfly this out, and I am going to get 6.04. Now, I didn't write the butterfly because I used my proportional trick. How do I turn 100 into 1? I just divide by 100. So I just did that same thing here. Dividing by 100 is like moving the decimal. And so I know that that's what that's going to be. Okay? So, question 32. An architect builds a scale model of a sports stadium using a scale in which 2 inches. Okay, so I got my scale numbers. I've got my inch numbers. I'm going to have top left be the scale in inches. That'll be 2. And I go ahead and I set up the rest of the proportion right now so I know where I'm going to fill stuff in later. Okay. Look, pal, if you ask me for a pencil one more time, I'm going to duct tape your little voice box shut and throw you over the desk. 2 inches represents 30 feet. So on my scale, and this time I put my scale on top. Now, you're thinking, well, the last time you had the scale on the right side, and now it's on top. Do I put it on a side or do I put it on a top? It doesn't matter. As long as your labels match, you can set this up any which way you want. In fact, there's 4 different correct setups for any one of these problems. Just like if you take a square, you can flip the square so that it's got this corner in the upper right, or you flip it up this way, and that corner can be in the bottom. I guess it's left, not right. You could flip it over this way, so that corner's in the bottom right, and you can flip it back that way. It doesn't matter. It all ends up, it's still the square, right? Same thing here. As long as it's a square, it's a square. The only thing that matters is the labels match. It doesn't matter where those labels are. So I'm going to go ahead and prove it. I'm going to set this up one way, solve it, and then set up a different way and solve it, just so you know it's safe. And then you'll feel confident, I hope. The height of the sports stadium. So here we've got the stadium. And this is going to be 180 feet. My feet numbers are over here on the right. It says, what is the height of the scale model of the stadium? So I'm thinking, well, maybe height's a better label. The height in real life is 180 feet. The height in inches on the scale model is, well, that's what I don't know. Okay. So butterfly this out. I'm going to do, don't forget the body of the butterfly. 180 times 2, which is 360, equals 30x. And then I just need to divide that. And I know if I'm dividing by 30, that I can just cancel out these zeros. And 36 divided by 3, I've got my 12 times tables memorized, so I know that's 12. And take another look. What if I wanted to start with the thing I don't know in the top left corner? That's fine. I say, okay, this is going to be the height and the height. I know it looks totally different, but remember, as long as the labels match, it's totally fine. So I've got the height and the height equal to the scale and the scale. Double check my labels. X and 2, what do those both have in common? What is the height in inches? So the X I don't know, and the 2 that I do know, those are both measured in inches. 180 and 30, Those are both measured in feet. 2 and 30 both came from the scale, and then X and 180 both came from the height of the model in inches, the height of the real one in real life. And then if I do the same multiplication, wait a minute, 30 times X is still 30X, and 180 times 2 is still 360. So we'll still just have 30X equals 360. I still solve it by dividing both sides by 30, and I still get 12. Ta-da! All right. Leon created a scale model, scale drawing, and I don't know. Is there any duct tape nearby? Well, no, not right on hand. I could go get some if you need it. Then do you have any pencils? Kids, you go work on these on your own. I need to cry. I'm being taunted by a talking pencil sharpener.